I think we should start. Uh, Today, our honorable speaker is Dr. Kausik Basak. Dr. Basak is presently working as an associate professor at the Center for Health Science and Technology, JIS Institute of Advanced Studies and Research, JIS University. He received the BTech degree in Electronics and Instrumentation Engineering from West Bengal University of Technology in 2008, the MTech degree in Medical Imaging and Image Analysis from the Indian Institute of Technology Kharagpur in 2010, and the PhD degree from IIT Kharagpur in 2015. He has over 15 years of research and academic experience, including postdoctoral research at the School of Medicine, Technical University of Munich, Germany, and at IIT Kharagpur. He has also served as assistant professor at Mahindra Ecole Centrale, Hyderabad, and as a visiting professor at Centrale Supélec, Paris, France. Dr. Boschak has authored numerous peer-reviewed journal articles in leading international journals, books, and book chapters. His research interests include machine learning and AI, medical image analysis, bioinformatics, antimicrobial resistance prediction, and transformer-based language models for sequence analysis. Dr. Boschak is a recipient of the TUM University Foundation Fellowship 2018-19, the postdoctoral mobility grant from Technical University of Munich 2017, and the visiting professor fellowship at Centrale Super Paris in 2017. So, may I request Dr. Boschak to start the lecture? Thank you.
Well, thank you so much, sir, for such a nice introduction. Uh, yeah. Good evening, everyone. I hope you have completed your work because the next watch is going to be very much enriched in machine learning and AI aspect. And if you can go through very properly, and if you have any doubts, if you can definitely ask questions about that. I hope like that will help you to develop any kind of novel machine learning algorithms in your field as well. So, without any delay, let me share my screen first. Yeah, so can you see my screen right now?
Yes,
Okay, so today's seminar will be on AI versus superbugs. So here I tried to show you that how machine learning, or in a broader sense, artificial intelligence, can be utilized to identify the drug resistance pathogens. So definitely, as you from the name, you can get an idea that it has a very good amount of uh, like uh, knowledge requirement in the biological domain as well. So I'm not going to tell you a lot of things about the biology in today's class because it will take a lot of time and a lot of basic knowledge as well. So I will try to focus more on the machine learning and artificial intelligence part, and how the algorithms has been developed, what are the basic components of it, and like how it can be actually implemented to the practical field to identify the drug resistance genes. So, like, starting with this particular aspect, AI. So today, in these days, we heard a lot of about buzzwords in the artificial intelligence, like starting from Chat GPT, or kind of say Claude, or like Google Gemini. So we are surrounded with a lot of different AI based applications or AI based tools, where knowingly or unknowingly we are utilizing different types of AI based applications as well. So let us first try to understand what is this AI actually. So when talk about this particular artificial intelligence, This is like kind of when we are trying to provide the knowledge that a particular human is possessing into some kind of machines or computers. What we try to mean that the machine or the computer will try to react or try to act or try to mimic the human behavior, and accordingly it can gather some kind of intelligence during this entire process. So artificial intelligence, it's a like of it's a entire thing that corresponds to a lot of aspects inside it. Like talking about today's world, like you must be come across to this Siri or Alexa, this kind of applications. So if you just think properly, this is not just one kind of work is happening, or there is not like only one algorithm is operating inside this particular application. So a lot of things are happening when you are just asking, say Siri, like try to play some song from the YouTube. So at the time you just say this particular prompt, so it will try to identify, like first the voice recognition will happen, then it will based on the keyword it will try to go to the YouTube and it will search that particular song, and then it will pick the song from the YouTube and then it will play. So a lot of applications are going on. It is not just only a specific task. Whereas when you talk about the machine learning, it particularly focus to perform a specific task, and over the time the algorithm will get its own experience from the data itself. So it will in a sense like it will try to learn on the data. So there is a differentiation between learning something and memorizing something, you know. So like learning means you try to gather some kind of knowledge over the time from the data, whereas memorizing means you are just matching something from the input to the output, you are just trying to matching something. So you can think about that machine learning is a kind of subset of this entire artificial intelligence. And what is neural network under this machine learning comes across? So it's a kind of specific umbrella of algorithms in which in today's world we are mostly focusing at. And under this neural network also we have this deep learning aspect, like uh, a much more complex neural algorithms which can solve the real world data and in more critical data, I should say, and at the same time it will try to give us more accurate output for a particular application. And one branch of this particular deep learning algorithm network is the generative AI, or in short we say it as the gen AI term, which particularly focus on the generation of newer kind of synthetic data. Okay, so synthetic data means like this AI or machine learning, whatever you just want to say, it can be utilized for multiple tasks. So classification, regression, like the natural language processing, then synthetic data generation. So these are the different types of tasks that we can do using this particular machine learning algorithms, and under which we have different set of algorithms also which are kind of fixed, which can perform, which can be utilized for to do some kind of specific task. And this entire world we can think about as the AI universe. Okay, so now we talk a lot about the AI universe on artificial intelligence part. Let us try to think about how it is evolved over the time. So I just want to quote over here the famous saying that what we want is a machine that can learn from the experience. And this is nothing but said by Professor Alan Turing during the year of 1947. So, if we go back in the age of time, let me take you back to the age of time, like say 1 million years of ago. So, what we see that during this particular Stone Age period, human tries to develop different kinds of what should I say? They try to shape different types of stones to do different types of jobs, like supplying the field, to hunt some animal, or even creating some fire. So this probably be the first time of they started utilizing their own intelligence. Now, in the last 10,000 years, we have seen that human or civilization has been much more progressed, and they have started utilizing creating different types of instruments by which they can create much more advanced solution, like plowing the field or creating some kind of infrastructure like that way. And in the last 100 years we have seen the utilization of steam engines, like which can carry lot of tons of heavy goods from one part of the their from one part of this world to another part. So like, and in the last 10 years we have witnessed, like we are sending robots in the other planets also, which can itself take some samples, and like it can create analyze some kind of own data, and it will send the data to the earth stations. So throughout this time, what I try to mean that we as a human being we try to extend our capabilities by developing different types of advanced machines, and we try to incorporate some our intelligence into those machines so that they can do a lot of critical tasks where we have some kind of physical limitations. It is like, if for a human being, if I am just giving tons of heavy materials, it will be impossible to carry from this point to that point, or it is very much difficult for a human being to survive in the other planets also. So we are sending a lot of intelligent robots which can do this particular task. So that we are trying to just overcome our physical limitations by incorporating our intelligence into the machines as well. Okay, so now in this particular today's world, we are observing a lot of applications in the artificial intelligence and machine learning in different sectors, like talking about healthcare sectors or financial sectors or law and judiciary sectors. So we have witnessed like there are huge applications of the artificial intelligence and machine learning algorithms. Why it is happening? First of all, over this particular era, means period of time, each and every sectors they have gathered a lot of data. Now these data are just acting as a backbone to these particular algorithms. So the more amount of data that you have, the better your algorithm will be. Definitely, data can be in any form, like structured, unstructured data. But the main point is, the more amount of data, the better your algorithm learning process will be. And these algorithms, when we are putting them to feed, we are feeding them a lot of data, they can gather a lot of good knowledges from this data, and they can do some very critical tasks which perhaps very much not which perhaps very much difficult for the human beings to perform. Okay, and in the same time they can create more accurate result as well. And the last point is, which is the inter-observer variability. Like this can be seen in a lot of medical domain applications as well. Like given a particular MRI or ultrasound image, different doctors have some say different opinion based on their experience and their expertise as well. But in the when we talk about machines, so they are developed based on some kind of ground data. Their knowledge has been developed based on some kind of ground data, and whatever be the data that you are giving as a new input, every time it will generate the same pattern or same output as well. So the percentage of inter observer variability is getting very much reduced when we are bringing this kind of algorithms into the play. Okay, talking about this particular application fields, like we have seen its huge applications in medical image analysis, bioinformatics, instrumentation part, then augmented reality, point of care analytics, big data analytics in healthcare as well. And in today's lecture I want to focus my development or like our work in this bioinformatics domain only. Now this AI or machine learning in its core, like it has three important aspects. First one is the algorithm, second one is the optimization, third one is the evaluation. Algorithm is the one which we basically develop and which can learn from the data. Learn from the data means, again I am telling you, it is not just memorizing. Like we have seen a lot of dedicated applications of the physics based models as well. Like if you remember, then we used to derive second order partial differential equation for that simple harmonic motion. So what it is actually is like, given some kind of any input, it will gives you some output. So it's a kind of dedicated mathematical equation present which can describe those particular system. But the problem with this our nature is only this kind of descriptive systems are 5%. More than 95% of the system that is present or happening in the nature, that is like purely non-descriptive type. So how to analyze them? So for those kind of analysis, we are bringing this concept of this machine learning and artificial intelligence. Yes, there are other ways to analyze them also, but what happens that, as I told you, over the time we have gathered a lot of data. We means each and every industrial sectors or like any research sectors as well. So, and machine learning has the advantage that when you have a huge amount of data, it can gives you a very good amount of output. So better not to focusing on any other kind of algorithm. People are focusing in this machine learning domain as well. And talking about the core at the heart of this machine learning, there are different types of algorithms present, like which perform some numerical functions like regression, neural network. Then we have decision trees, random forest, then nearest neighbor algorithms, hidden Markov models, Bayesian networks. So these are the different types of algorithms which are present under this machine learning territory. And when we talk about the learning, you try to keep it in mind that every time when we start this learning process, not exactly from the very beginning, the algorithm will give us a very good amount of output. So the output may be full of error as well. So our task is to reduce the amount of error so that the accuracy get more and more and more from iteration to iteration. And how to do that thing? For that, we need the second important category, which is the optimization techniques. So we have a lot of optimization techniques as well, like gradient descent, dynamic programming, then rule learning, genetic algorithms. So these are the different types of optimization techniques that we can implement to reduce the error. And while reducing this error over the iteration, that means the algorithm is learning on the data. Means there will be some kind of, I think in the previous like lecture you have gone through the supervised and unsupervised learning. So in the supervised learning, you see, like, you have some kind of label data, like for the output you already know. So when the output is no, now during the training process, what we generally do is that I try to see how the model is generating from the iteration 0. It may be full of error. I am telling you again. Now, my task will be to reduce the error as much as I can. Definitely the error cannot be zero at the same time, because ultimately there will be a lot of noise present in the data which can like reduce the accuracy part of this model as well. Or sometimes, like, if we do not properly choose the model, because each and every model has their some kind of advantages and some limitations as well. So at that point of time, the results will definitely like lose from that aspect. And the third point is the evaluation. Like, one, when we can say that a particular model is trained or the model can be utilized for practical task. So based on this evaluation category, so for the evaluation we have different metrics like accuracy, precision, recall, like then entropy, squared error. So these are the different types of evaluation metrics based on which we can say that a particular algorithm is now ready or trained and it can be deployed for the practical field. So these are the three important aspects which we need to implement while creating any kind of machine learning algorithms. Now, let us try to see that how a particular learning systems can be designed. So, what we have on this particular side is basically the problem environment. Like, the problem environment means it can be anything. Or whenever you are working in the healthcare sector, say medical image analysis, so MRI image analysis. So MRI image will becomes your problem environment. And then what you try to identify out of it, so that becomes your problem. So from that problem environment, we need to find out some kind of attributes. So these attributes in machine learning domain, we say it as the features. Okay, so if you're lucky enough, then you will be sometimes supplied with these features. If you are unlucky, then you need to find out these features from this problem environment as well. Now once these features will be find out, so that the first task that we need to go for pre-processing task and lot of things. So these pre-processing again can help us to reduce the error or noise present in the data and all that. Now, once it is done, what we do, we quickly divide this input data into training and testing part. Then training data would be utilized for the learning system to create the knowledge. Now, once the knowledge creation is done, then the next task will be utilizing the testing data to check the performance. And accordingly, it has three important phases. So first of all is the training phase, which basically takes a lot of time, because in this particular sense, like during the training is very much important. Like in machine learning environment, the training is the most important part. The more amount of data that you can supply for the training, the better your algorithm will learn over the data. Again, learn over data means it will try to identify the hidden patterns, the hidden associations between the features or between the different kinds of key attributes. Now, when the training phase is done, what we do, we just check whether the algorithm is been providing us a good results on the testing data or not. Sometimes it may happen that the training performance metrics are quite good, but the testing is providing us a lot of error, like the accuracy or precision is not very good. So they in that time, during that time, we again have to go back to the training phase. We need to check how, whether we have done any kind of wrong thing, or we have done any kind of wrong assumption or not. So then accordingly we need to modify the algorithm. Again we need to do the training process, and again we need to check the testing. Until unless we are getting a very good score in the testing phase, we cannot go forward. So once the testing phase will give us a very good output, then it will be the next phase when we can deploy our algorithm in the practical field. So that's the entire process how a machine learning algorithm can be trained from its practical utilization in the deployment stage. Okay. Now here I am just showing you one important aspect of this data splitting. How do we perform this data splitting? There are different types of ways by which we can split the data. Like I told you, given the input matrix, we need to divide the data input matrix into training and testing part. So how do we do actually? I'm just showing you one particular aspect of it. Okay, there are different types of aspects present. You can choose like your own way as well. So suppose this is a particular kind of feature matrix present. Here, these columns, they generally represents the features, and these rows, they generally represents the samples. Okay, I'm talking about this kind of structured data because it is easy to understand. But at the same time, I need to keep it in your mind that there are unstructured data as well. For example, like image. I hope I think like it has already been covered in Professor Kishore's class, and the unstructured data, like it has image, then audio, then video, all these are comes under the unstructured data, and utilizing them for the machine learning algorithm is also another aspect which I am not covering over here. So I'm just focusing on the structured data at this point of time. So what we do, we just do apply holdout method at the first. So we keep the 80% data for the training purpose, and we keep our 20% data for the testing purpose. You have to remember that this 20% data is not taking any kind of data out of these training samples. Like there won't be any kind of overlapping, because the testing set should be as independent as the training samples as well. Now there are different ways. I told you, you can utilize this 80% data entirely for the training purpose of the machine learning algorithm. Sometimes it is advised that if we can utilize some cross validation techniques. Cross validation means these entire number of samples. For example, I am having say 1,000 number of samples in the training. So this entire number of samples is divided into say 5 buckets. So this is a kind of five-fold cross validation. I can utilize tenfold cross validation as well. In that case, this thousand amount of samples will be divided into 10 buckets, you can see. So in five-fold cross validation, here I'm just showing you an example of the five-fold cross validation, because one, two, three, four, five buckets you can see over here. So the four buckets will be utilized for training, then the last bucket will be utilized for testing. Then in the next phase, the first three and the last bucket will be utilized for training, and this fourth one will be utilized for testing. So this, like this way, this will happen. So in the next phase, then first two and the last two buckets will be utilized for the training purpose, and the middle one will be utilized for the testing purpose. So this way, the cross validation will happen. That means we are checking any kind of possibility of randomly selecting the data, and we will check. So like for this first fold, so this is fold 1, this is fold 2, this is fold 3, this is fold 4, and this is fold 5. So for the fold 1, we will get a set of evaluation metrics like accuracy, precision, recall, all these things we will get. Similarly for the fold 2, we will also get similar kind of results. And at the last, when all these five folds will be done, then what we'll do, we'll just take the average of these metrics to get the final answer. Now when this particular set of matrix will gives me a satisfactory results, then the next phase will comes on the testing. So the trained model will be utilized for this testing purpose only. Okay. So now let us focus on the case study part. So with this basic introduction of this how ML machine learning model can be developed, I am just directly going to how we have worked on identification of escape specific antibiotic resistance genes. So let me just tell you a little bit about the biological aspect of it. So why it is so important again. So antibiotic resistance is a big research area in today's world, because you see, in the last month we had one conference with ICMR, that in which there are various doctors present, and like a lot of doctors, they presented the practical difficulties. Like they see people, see patients which for which they have some kind of like proper processing of the cure, like how what should be the theranostics that could be utilized, but at the same time they cannot utilize any kind of specific medicine or antibiotics, because the results, antibiotic susceptibility test, AST, so this shows that those patients are kind of susceptible or resistant, sorry, not susceptible, they are resistant to a lot of different categories of antibiotics. So those antibiotics cannot be utilized on those patients only, and the number is very huge, it is not minor. And why it is happening, like due to us only. So like in today's world, in country like India, we have we can get the antibiotics over the medical shops only, without any kind of prescription. And no, unknowingly, I would say, like most of the time it is unknowingly that we take any kind of antibiotics, whether it is required at all or not, and that is creating some kind of resistance to the bacteria present inside our body. So let me tell you that there are huge number, beyond like million number of bacteria present inside our body. Most of the bacteria are kind of good bacteria. They are helping our ecosystems to properly function. But when we are taking this kind of antibiotics for which we do not know what could be its effect, these antibiotics will like kill the good bacteria, and eventually when this kind of ecosystem is kind altered, then what happened, the bad bacteria is kind of mutated, they kind of create resistance on those kind antibiotics, for which the patients like recovery percentage will get reduced. So, and this number is quite big. In the next slides, you can get an idea. So you see, like overall in the whole world, like 80% of the deaths related to antimicrobial resistance, or in short, we say it as the AMR. So this is, and $23.7 billion has been kind of expensed uh, to like rectify this particular type of error. And within India also, the mortality rate of the people is 13.1%, and due to that we are reducing 4% of our GDP each and every year. So it's a kind of very huge matrix, you see. And this antibacterial matrix, when we talk about it, there are different types of bacteria are present. What we are particularly focusing in this work is the escape group. So it's a six specific bacteria which are very much notorious and which can create a lot of troubles in our human body as well. So these one are the Enterococcus faecium, Staphylococcus aureus, Klebsiella pneumoniae, Acinetobacter baumannii, Pseudomonas aeruginosa, and Enterobacter species. So these are the six pathogens or bad bacteria which can create a lot of troubles in our human body. So mainly one another important aspect is like we are doing another research on how these escape pathogens are kind of surrounded or get spreaded in the human beings. What we see, you won't believe, like a lot of these kind of infections they comes from the ICU, because these bacteria are kind of developed random, like very much rigorously in the ICU environment as well. So that's why these pathogens, they called hospital acquired infections, like they found mostly in the hospitals as well, you see. Sometimes it may happen, you have seen in your, you may have seen in your like surrounding people as well, that some patients went to ICU, when he get outside from the hospital and comes to the home, the patient is showing some kind of different troubles, other troubles as well. That is due to this kind of bacteria. Okay, so what we are trying to work over here is, so you see, there are some kind of specific genes in this bacteria's genome present, which actually get evolved and shows resistance to this antibiotic. Now, what we try to identify is, uh, can we develop some kind of machine learning algorithm by which, given a genome sequence of this bacteria, it can easily identify what are the escape specific genes present. From there we can say that this bacteria has a tendency to get resistance to that particular group of antibiotics very easily, because as of now you can do it simply by doing these like antimicrobial susceptibility testing, but the results may come after like 5 or 7 days. It can and the like testing itself is very much costly. So definitely, to reduce these particular two aspects, like time aspects and the cost aspect, what we are trying to do, like we are trying to develop some kind of algorithms by which the algorithms can itself say like, okay, this particular human has having this particular genome bacteria, and these bacteria can be resistant to this particular group of antibiotics, so that that particular presence won't be applied with those antibiotics, they can be treated with some different other generations of antibiotics as well. Okay, so now entirely, now I'm that's all about the biological thing. Now let me just take you to the like technical part of it, like the algorithm part of it. So the process is quite simple: data acquisition. So for the data acquisition, like I told you, like in this today's world we are surrounded with lot of data, billions of data. So now just we have to utilize them in a proper way. So NCBI genome database, they have a lot of this kind of antibiotic resistance genes database presents, which will be collected throughout the world. So we collected this kind of data from the NCBI genome, because for the training purpose we need a lot of data, I told you. And for the clinical part we cannot create this much of data because it takes years of time to do the, to take the samples, to do the sequencing of it, and then doing the finding out the good sequence out of those analyses, and then applying the lasers. It will take a years and years of time. So what we do, we take the database, NCBI genome database, data sets. And after that there are some kind of pre-processing is needed, because what we directly downloaded, that can be fed to the machine learning algorithm. We need to do some sort of analysis, like what are the, so these genome databases, they are taking combining all the different types of bacteria as a whole. Now from there we need to identify what class particular genome belongs to. So for that we do have this kind of cd hit, core finding, and rgi, resistance gene identification tool. So these are kind of standardized tools that are utilized in the bioinformatics domain. Now, once this pre-processing done, then the next part will be encoding. Like you see, when we talk about here, we are utilizing the gene sequence data. And if having a very basic knowledge about it, so this gene sequence is basically a combination of four nucleotides, A, C, T, G. These four nucleotides are basically helping to create the DNA. Okay, so it's a kind of, you can think these gene sequences as a kind of natural languages where only four alphabets are present. Now you see, like whatever like conversation we are happening, or whatever words I am pronouncing, or whatever words we are writing, they are consist of 26 alphabets. Now from there you see this data set is very much easy, so encoding becomes very much easy for this kind of data. Now once the encoding is done, then it will go for the machine learning application, or then it will comes to the how machine learning algorithms can be developed on this particular task. Now, this is a small description about the data set. So what we collect is the number of strains. So these six bars are corresponds to six different bacterias over here. So I'm just showing you numbers, that how much number of strains we have collected from the NCBI databases. And out of the strains, the first we find out the sequences. Here you see in millions. So 1.66 million, 3.24 million. So number of sequences are quite huge. And that is the best part, like this many number of data, I can very utilize it for developing my machine learning algorithm. Now, once the sequence I found out, then we need to find out the clusters and the cores. Cores are basically to check like whether there is a kind of commonality present or not. Like we try to identify what are the common like sequence patterns are present within a particular bacteria. So I am working with them only. So we got this many number of cores out of it, and clusters is basically helping us to find out like which sequence forming which clusters and all that. And here we are finding out these resistance genes identifier. That means this is providing us the actual class, the labels of this particular data. So these are the data that we gathered, and from here we gathered that for each and every bacteria how many classes are present, like that is how many labels are present. Okay, so now the next part is the encoding. So KMR encoding, it's a basically very standard process to convert any kind of nucleotide sequence into a fixed numbers. You see the problem with the sequences are they are variable length. Like one sequence have some kind of say 400 base pairs, so another sequence it can be 1000 or 2000 or 300, any kind of base pairs it could be. So the beautiful thing with the KMR is every time if we utilize this KMR to encode these particular sequences, it will return us some kind of specific fixed matrix. How it is giving us? Let me show you. So suppose this is a DNA sequence. It's a pattern of A, C, T, and G. Randomly, I have chosen that thing. And KMR, for example, I'm taking K equals to 4. So 4 means using four nucleotides, how four combinations we need to make. So how many combinations we can create? It will be 4 to the power 4, and that will be 64 combinations we can create. So if it is k equals to 6, I can consider, then it will be 4 to the power 6. That means it will be something like 4 to the power 6 number of combinations that I can create. Okay, so A is the first combination, then AAC, AAG, Then this way, these many number of combinations that I can create. Now, for the encoding purpose, what I will do, I will try to find out that what are the consecutive patterns it will get. So you see the first pattern is ACGA. So this will be counted as 1. So this pattern will be counted as 1, the rest of the pattern will be 0. Then I move the window to a next slide. I'm putting the stride as 1 over here. So in the next pattern would be CGAA. So now here the count will be made as 1 here. So this way, as we move on for the 4 combination based like window, then we will try to find out lot of different patterns will be created, and this will create this kind of 4 bar count matrix. You see, for this particular sequence ID, so there are different types of sequence IDs present. Not necessarily I am showing you over only 4 or 6, but actually there are lot more IDs are present, and these are the matrix that will be generated. So this is my feature matrix over here. You see, now the sequence has been converted into a numerical matrix. This numerical matrix definitely, as you know, like it can be directly input to the machine learning algorithm, because as in the nutshell, like the machine learning or the machines cannot understand any kind of text or say alphabets or any color, anything. It can only understand the numbers. So this kind of encoding gave us this kind of patterns, and these patterns can be utilized as the input to the machine learning algorithm, and this AAC, these formats becomes the features. So in this algorithm, what we come to this point, we have created one 4-mar matrix, and based on the sequence that I have, and for each of these sequence ID, we also have its corresponding class labels. So basically this is a supervised algorithm. So in the supervised algorithm, what we have the numerical representation, but in the class we only have what this particular sequence is resistant to. Means what are the different antibiotics this particular sequence is resistant to. So that means we need to convert the class into some numerical representation as well. So for that conversion, we can utilize label encoding, as it is very much easy to implement. So label encoding for the class labels we can implement, and for this kind of sequence data, we are converting it into a KMR matrix. Okay. Now there might be some question like, can we utilize directly this sequence, DNA sequence, to as an input to the any kind of machine learning algorithm? The answer is yes, definitely, because in today's world, the machine learning or artificial intelligence, it has been improved in such a way that we can take any input. We can give image as its input. We can give this DNA sequence as a direct input to the algorithm. But they are the different set of algorithms. Like I'm talking about LLM, large language models. So where we can directly give this sequence data and it can analyze it. But it what we are focusing right now, it's a kind of sequence based algorithm. I will come shortly inside the algorithm in detail. So in that sequence algorithm, we need to convert the data into some numerical form. Then we can give that numerical data as an input to the model, and the model will try to learn on it, and it will try to give us some kind of results. Okay. So now coming to the next part. So this is
Dr.
the
Basak, may I ask one question?
surely, surely.
Yeah. In the previous slide, this slide, the number represents the number of times this sequence appears in a particular DNA sequence, right?
Yes. So
Okay,
this combination, this is basically a
this
4-mar
combination.
combination. The
Hmm.
how many times it appears in this particular sequence. So this is a
Okay,
counts, or you
this is
can
the
say
count.
frequency.
Right. And what do you mean by 4 marks? Why it is marks? And
So it's the Mars means the basic nucleotides, means over here only four nucleotides are present. So K Mars means K value we can choose anything. Okay. But the problem is, you see, when I'm taking K equals to 4, it will create 4 to the power 4 and 64 combination. Okay. Now, if it goes to 4 to the power 6 or 4 to the power 8 or 4 to the power 10, you see the number of combinations grows exponentially. So the amount of training time will be huge, and the hardware requirement will also get huge. So that's why we have to, means till now, practically speaking, like I have worked with 10 Mars. That means using some kind of Xeon servers that we have in our institute. So we have worked on that, but it is taking like 3 days, 4 days amount of time to learn, to train on the data, because lot of features. So over here you see 64 features are generating. So in this particular type of data, what is one more important aspect, thank you Kishore said, like you just remind me to tell this thing, that this feature matrix is very important, the dimension of the feature. So, and how the dimension can be defined? The dimension is how many number of features that you are utilizing. And based on the dimension of the data, the computations becomes very much used, because you see every computations in the, whether you are saying Python or MATLAB or whatever it is forming in the matrix form. Okay. So bigger your dimension, the more your computational time and the more hardware requirement will be necessity. Okay. So now it does not depend on how many number of samples are there. Number of samples you can give as much as it will be good for a particular algorithm to train. But at the same time, if your dimension, that means your number of features in increasing in this exponential way, that means the requirement becomes very, very huge. Okay. So that is the process. That is why, like I'm showing you over here, only k equals to 4, because in my laptop, even k equals to 6, it will take a lot of time to train. And what I'm going to plan, like I will show you one code there to take some part of data to run on it, so that it can give quickly result. But when we run the data on this former matrix only, it took like nearly 1 hour of time to train. Okay. So yeah, I hope I can answer your question, Kishore sir.
yeah,
One more thing.
ha, ha,
Sorry, if you are
uh,
finished, so please finish your question.
okay, okay. So one can use k equals 2, but this will be oversimplified, right?
K equals to 2.
Yes, that will be oversimplified, I think.
K equals to 2, sir, actually it's a dimer kind of thing. Yeah, definitely it will be oversimplified. Like the thing is, you see, these are, what is our goal? We try to identify some genetic sequence pattern by which we can say that the antibiotic is resistant to the, sorry, that particular bacterial gene will be resistant to this group of antibiotics. Okay. Now when we sequence, the gene comes in the form of say 100 or 150 base pairs. Like if you are utilizing this next generation sequencing machine, so every reads comes as a 150 or something like that base pairs. Now under this particular thing, ideally it should be good, the bigger k I can take, like k equals to 8 or 10, the more it will be good. But at the same time, I just told you the processing time will be very much huge. Okay. So smaller, the better number representation you can get, but actually it will not give you any kind of good sense, because ultimately my task is to find out that which feature are most significant
Important.
from this data, and which can gives me to this particular class of resistant antibiotic.
Okay, okay.
Okay. Yeah. So anyone else was asking something like
Yes, just one thing, that this is only a sample data that you are showing, right? Because all the columns are having same data for different
yes, yes,
sequence,
yes.
right?
This is basically a sample data. I'm just showing you.
Okay,
I will show
okay,
you a problem former matrix like
Okay.
once the lectures will be like once when I will going to show you the code, I will show
Hmm.
you one true former matrix with 64 number of features as well. But this is just a part of it, just to show you that how the counts are appear. Okay.
Right. I understand. Thank you.
Okay. So yeah, so now this is the network architecture that we developed to like learn on this particular data and to give us some kind of class output. Now till this point, what we learned that we have a former matrix. Each rows corresponds to the different sequences and each column corresponds to different features. These features are nothing but the four k-mars or 4 mars you can say, and associate to each and every sequence will also have the class. And what are this class? The class represents this particular sequence. This bacterial sequence is resistant to which group of antibiotic. Okay, so this is so far the data that we have computed. Now let us work with this particular thing. And I also told you that the class has to be converted or encoded using some kind of label encoder. So now this is the actual network that we have developed. So this is the KMR that we are taking as the input. So the main, so this particular network has two important part. One is the auto encoder part, and another one is the deep neural network based feed forward network. Okay, so don't worry, I'm going to explain both of the things very clearly. So in this autoencoder, we have the encoder and decoder unit. This encoder unit will try to compress the input data and create some kind of representation. Like this representation, now this decoder part will work in a just opposite way the encoder worked. So from the representation layer, it will try to recreate the KMR matrix. And at the same time the model will try to find out the reconstruction loss. You see, the lower this particular reconstruction loss, the better the creation of this KMR pattern and the better the formation of this representation layer. So what we try to do basically, from this huge amount of data, we try to create some kind of representation layer. So autoencoder, this is basically a representation learning. So from the huge amount of input data, it will try to give us some kind of meaningful data which will actually be utilized, and the dimensionality of the data will definitely reduce. Say for the input dimension, if I'm having say 64 in the representation layer, the dimension will be say in a 10 to 15 like that. Okay, so the dimension of the data is getting very much reduced. It will try to keep only the important part, which only the important features in this representation layer. Out of this representation layer, out of these features, when the actual KMR matrix can be reconfigured. Now once this representation layer creation is done, then this particular layer will be utilized for the classification part. So this is the classification area. So this is the feature extraction part. In the representation layer, or sometimes in some of the books it is known as the latent layer. In this particular layer we try to create some kind of feature extracted features, and then these extracted features will be utilized for the classification. So this is the classification unit, and at the output of this classification we will get the class, means the resistant antibiotic groups. Okay, so let us just go and think about what is this particular LSTMs and autoencoder and this feed forward network is actually happening. So let us take a dive into this neural network a bit. I will come back to this architecture again, but for the time being, let me just tell you a little bit about these different types of neural networks. So artificial neural networks, this is basically I'm providing you a multi-layer perceptron model. Multi-layer perceptron model means from the name you can get an idea that multiple layers are present. So this is the input layer where I'm giving the input directly. Then there is a hidden layers present. These hidden layers are doing some kind of operation, and then there is a output layer. From the output layer we'll get the final output. So this is the in general general architecture of the multi-layer perceptron model. Let me tell you that yeah, when it was like originated, this artificial neural network, say in the year of 1970s, I guess. So it was started with a single neurons. So that is known as the single neuron perceptron or Rosenblatt perceptron. It is given the name after the famous mathematician Frank Rosenblatt. So that perceptron is known as the Rosenblatt perceptron. But what we are discussing over here is the multi-layer perceptron model. Multi-layer perceptron means there are multiple number of layers present: input layer, hidden layers, and the output layers, and each layer comprises multiple neurons. So these circles that you see, these are neurons, and each neuron, they have two basic operation. One is the linear sum and the second one is the activation function. So these each and every neuron. Now you think, so see, this is not a neuron, this is just an input node. Neurons are this and this. So this is the first hidden layer neurons, this is the second hidden layer neurons, this is the third hidden layer neurons. There could be multiple other hidden layers also. This is enormous. It basically up to you or the designer or the programmer, means how many number of hidden layers he or she want to take, or how many number of neurons in a particular hidden layer he or she want to keep. So it entirely up to them. Okay, so there is a enormous opportunity that you can create your own multi-layer perceptron model. This is not a fixed model. So that's why I'm saying this is a kind of generalized model that I'm just showing you to express how it operates. And each neuron, it has two basic operations. The first one is the linear sum. You see these x, these are the input. These w, these are known as some kind of synaptic weights, and b is known as the bias. Okay, so different inputs are multiplied with some kind of weight and they are summed up. That means you see some kind of projection I am creating in this V, where different input has different contributions, and these contributions can be derived from this W. And there are obviously some kind of bias, because if all these are zeros, then there should be something in this output. So some definite bias we can keep. Sometimes this bias could be zero as well, no issue. Sometimes some positive value, sometimes some negative value, any value it can take, but we generally keep this bias. Like you see, like y equals to mx plus c. So c is basically standing the that bias over here. Here this mx. So this is a kind of linear solution. So by doing some kind of linear sum, this is a matrix representation of this linear equation. So by doing some kind of linear operation, so I am trying to project this x input into a new dimension v. So this is a kind of linear projection of the input data into another dimension. Okay, and the second function is the activation. So whatever output the summation will generate, that will be the input to this activation, and the output of this activation will go to the next neuron. So each and every neuron like this way will perform these two basic operations. Now this activation is some function phi which will operate on this projection, and it will create some kind of another values. So basically you see this is a type of non-linear operation. So this is a linear and this is non-linear. So why this artificial neural network is becoming so popular, you see that it can target both linear and non-linear relationships inside the features present. There are some applications, algorithms present, like which can only focus on like linear relationships. There are some application algorithms which can focus on some category of nonlinear relationships. But here Now, when we are going to the non-linear domain, you see the non-linearity itself is huge. Whether it is first or second order non-linearity, third order non-linearity, some kind of Gaussian non-linearity, it's the opportunity is quite huge. Now, with the help of a little bit, a few activation functions, 5 or 6 activation functions are present in practice. So we can project these nonlinear relationships and we can identify the nonlinear patterns present in this input. Okay, so that's what I said, like this artificial neural network will learn the data, the hidden parrot patterns between the data, how they are actually co-evolving or correlated something. So now if we just combine these two equations, you see for the layer J, here I have written layer J, layer K, layer L. So this is the summation. I stands for input and this J stands for this jth layer. So Yj is some function of Sj. Again, you see this Sj, this Yj will be the input to this. So this layer K, the summation will be W transpose Yj. This Yj that is getting from this activation. And again it will generate another Yk. Now this Yk will be the input to this layer L, Yk. You see, it's a very good and beautiful thing. Like once you solved one equation, it is just a chain. So every layer, every neuron will do the same operation and ultimately will get the Y output. Now talking about these activation functions, like I told you, so these are some of the very important activation functions. In like I can tell you, like for the past 15 or 16 years, I'm like working in this particular field, and like I have developed different types of algorithms. Not like I have test trained with a lot of different algorithms at all, but till now whatever algorithms I have utilized, like they are mostly operated with these 5 activation functions as well, like they are good enough. Okay, apart from that there is also Gaussian activation functions are present, but that is very less I have utilized, but these are the 5 more utilized activation functions which can track the non-linearity present inside the data. So first one is the threshold. Threshold, you see, like it's doing some kind of thresholding operation. So based on some this zero, we can manually choose which threshold value we want to keep, that we can manually choose. Then identity function is present. Then sigmoid, it's mostly utilized, like when we talk about multi-layer perceptron model, mostly the sigmoid function is utilized. Then there is a tan hyperbolic function. We will shortly see where these tan hyperbolic functions are utilized. Then there is recurrent rectified linear unit. So this is also mostly utilized in case of deep learning or convolutional neural network, those kind of system it is mostly utilized. Okay, so these are some sort of activation functions that we mostly utilized in case of developing machine learning algorithms. Now let us talk about the how this training process will happen. So we give the input, then there is an input layer. So from the input layer, you see each and every input is getting giving its own output to this hidden layer. I am, for the simplicity, I am considering here only one hidden layer is present. Okay, so now this input is going to this neuron, going to this neuron, going to this neuron. So all the inputs are going to all the neurons. So this kind of network architecture is known as the fully connected network architecture. That means where all the uh, in output from the previous layer is getting input to this near current layer. There is no connection is off. Yes, you can manually switch off some particular connection, but at that point of time it will termed as the partially connected network. You can do it, but what we are talking about, it's a fully connected network, and often this is known as the feed forward neural network, because this is the forward pass. You see the information is flowing from left to right. So input, then some processing will happen over here, some linear sum followed by activation function, then this outputs will be give to this neuron, again linear sum, activation function, then final output will be generated. So inputs enter into the input layer, then each neuron performs linear sum followed by activation and fires its output. Then again at the output layer, same. So I told you these are not neurons, these are just input nodes. These are neurons, and this is also a neuron. So in the output also, it will similar way perform first the linear sum, then the activation function, and we will get the output. Now you see there is a desired output and some predicted output. Okay, because I told you these most of the artificial neural network, they are the supervised learners. There are some kind of specific exceptions which can be worked as a unsupervised, so there are few neural networks present which can work on the unsupervised data as well, but mostly these artificial neural network, they are developed targeting the supervised data. Okay, because there are some certain advantages of it. We can directly optimize the result. I am coming to that point. So you see there is a desired output and there is a predicted model. Prediction is the model output. So what I will do, I told you that it is not necessarily that after the first iteration we will get the right prediction. If we are getting, we are lucky, but what happened in practice, we mostly are unlucky. Let me be very honest with you. So that's why like we do not get every time the prediction as similar to the desired one. So definitely there will be some kind of error. So that will help us to create, to train the model. So what it will do, the error will be computed, and now I am taking the second component. If you remember, I told you at the beginning there are three important components. First one is the algorithm, second one is the optimization rule, and the third one is the measurement matrix. So now I am taking used utilizing the some kind of optimization rule. So a very famous algorithm in this, which is known as the back propagation algorithm. I'm not going into the detailed mathematical part because it's really complex and it will take a lot of time to explain over here. So I'm just showing you how basically it can be done. Okay, so the error will be computed, error will be desired minus predicted. Okay, and we will apply some optimization rules, say gradient descent, the simplest one over here we can utilize. So it will create some kind of error formula, some kind of gradient means some kind of error with respect to some parameters. Now over here in the network, what we try to train, you see, I am saying you this is the training process. We try to train the parameters, and what are the parameters? The W and the bias, the weights and the bias, those are the parameters of this network, and those parameters need to be trained. That means they have some kind of numerical value, and that has to be finalized or optimized based on this optimization algorithm. So now these gradient descent, if I am applying, so gradient of error with respect to what with respect to these weights and bias individually. So now these gradients will be computed, and it will utilized to alter the first the weights and bias of this neuron, because this error is directly connected over here. You see, using this error I cannot directly apply to alter the values of weights and bias over here because there is a via connection. So first I need to moderate the weights and bias for this neuron. Then once this neuron is done, then we have to take that knowledge and we have to moderate the weights and bias in this neuron. Okay, so this is how the back propagation process is actually happens, and that way, like if you have more number of hidden layers, uh, some, can you please mute yourself? I think some mic is on. Yeah, thank you. So this is the way that how the error can be utilized, and it will be back propagated. It is just reverse. In the forward path, the information flows from input to output. In the backward path, that's why it is called back propagation. So the error, the gradient of the error, it is propagated from output to the input, and that way gradually by layer after layer the weights and bias will be updated. Okay, so this is the back propagation rule, and this is how the artificial neural network will be trained. So these are some sort of important neural networks that I'm showing you over here. There are numerous, like lakhs of number of neural networks are present. Even no one can complete of what are how many types of neural networks has been developed so far. So I'm just presenting you some of the very important and different types of architecture. So feed forward network that I just discussed, it has input layer, it has hidden layers, then the output layer. Okay, so generally this feed forward network is utilized for classification and regression problems. Okay, remember this, because I told you while discussing about the network architecture that we developed for this ARG classification. So the feed forward network is utilized for classification purpose. Now there is some convolutional neural network which generally utilized for image analysis, because it can take directly input as an image. So image, even if it is an unstructured data, we can do not need to convert or find out the feature explicitly. We can give the input as an image to this type of network, and it will create its own, it will find out its own feature set, and from there it will do the classification. So mostly the convolutional neural network is utilized for the image analysis or image classification. Then there is some kind of recurrent neural network. It is mostly utilized for sequence analysis, sequenced type of data. Like I told you, there are different types of data present. If it is image data, then you can choose for convolutional neural network. If it is like a sequence data, like time series data, like this way, so it you can utilize some recurrent neural network. Because you see, I told you in our case the input data was DNA sequence, so I am going to utilize this recurrent neural network for our model development. Then there is generative adversarial neural network, so it's a kind of different sort of application in as a whole. Like this kind of architecture is mostly utilized for synthetic image generation. Okay, so you have some generator model and discriminator model, and by varying these two parameters or two models, we are creating a lot of synthetic data. So in these days you are might be heard about deepfake or any kind of AI based images. So basically generative adversarial network, or in short we say it as GAN. So this GAN can be utilized to generate this kind of any kind of fake images as well. And then there is autoencoder. Autoencoder is basically a representation learner, where it creates some representation layer, and based on that representation, we can find out what are the minimum amount of data that can be good enough to represent the original input data. So this kind of architecture is mostly utilized for compression. So can I take a 2 minutes of break, because there is a huge cyclone kind of thing is happening. Just I'm sorry, very much
Sure,
sorry.
sure, sure,
Uh,
sure, sure. Okay, sure. That's it. That's it.
Hello. Yeah, I'm really sorry because suddenly it appears that like I had to close the windows and everything. Anyway, so let us come back. I hope you can hear me, right? Hello.
Yes, sir.
Okay. Okay. Thank you. So what I'm going to tell you right now is the recurrent neural network. So this is a kind of symbolic architecture what we just try to represent the recurrent neural network part. So this H is basically a type of layer of neurons. It is a single layer of neuron. It's mainly said as the hidden layer. X is the input and O is the output. Now, how this particular thing is happening? You see, the problem with this feed forward network is when I'm dealing with some kind of sequence, the problem is uh, the number of input in this kind of feed forward network is fixed. Now, if the sequence length is varying, then accordingly we need to vary the number of inputs. We need to change the network architecture. And when I'm changing the network architecture, then it will be a big deal that all these weights and bias has to be changed again. So a simple single feed-forward network, it cannot be applied for any kind of sequence. Like say I'm talking about different sentences or different time series data. So this kind of analysis, so that's why we basically introduce this particular recurrent neural network. Lot of applications of it you have seen, like whenever you just go to the Google and type something, you will see some kind of future generation it is giving us, like some auto generation of the sentences it is happening. So like then language translation, whenever we are writing, we want to convert one language to another language, then whenever whatever we are writing at the side window, some kind of translated version is appearing. So all these kind of applications are happening using the help of this RNN. Okay, so natural language processing, then sentiment analysis is one more example, like in Amazon, Flipkart, all these things you will see there are a lot of reviews are present. Now, how to convert these reviews into the some kind of points, say in the scale of 5 or 10. So this is also happening using the this kind of recurrent neural networks. So how it is happening? It is actually, the model is very simple. This is a hidden layer. It consists of some set of hidden neurons. Now I am giving the input and it is generating some kind of output. Okay. Now in this thing, what is happening? So the input becomes word by word. For example, let me gives you this particular sentence. Kausik loves machine learning. Now, how these things will appear? So, Kaushik, first word, it will be vectorized. Like I told you, machines can only understand the numbers. So, first the word will be vectorized. Any kind of like one hot encoding or what to vec. This kind of algorithms are present which can vectorize any kind of word into a numerical representation. Okay. So now this numerical representation will goes to the hidden layer. So these are the neurons. Now this hidden layer will generate some kind of attributes. This H quotient. Now this H quotient will be again given as the input to this layer also. So there is a recursion. You see, these are not two different hidden layers. It's the two different time steps. So that's why I told you for time series data, this kind of RNN can be very much utilizable. This is the single layer. This is the single hidden layer present. But there is a recursion. Every time for every word, the model parameters or the hidden set parameters will be recursively fed back to its own in as input. So now when the next word comes to the same hidden layer, now I'm having the knowledge of the previous word and the new word. then it will generate a new hidden set of parameters for the age labs. So now this age lab comprises both things, this age Kausik and knowledge of this Kausik and labs. So you see, this is a meaningful sentence, right? What I am trying to say, like, if I would tell you that how are you, so this becomes meaningful to you. If I am telling you or asking you, you are how, does it making any sense? It is not, because sequence is important. In DNA sequence also, it is very much important, like which nucleotide is happening after what. That pattern is important. Okay, so that's why this kind of uh, time sequence pattern where previous timestamp has some specific like say um necessity or implications of the current stamp, then there this kind of RNNs could be very much utilized. So you see, when I'm talking about these labs, so that S is present, right? So because this Kaushik is a third person over here. Now this is entirely depend on what the previous word it is. Are you getting my point? So that is what, like, loves, it has having some kind of attributes from the quotient. Now in the next machine, it has some attributes from the H loves. Now H love has the information from this and this as well. Now when I'm going this way to the last word learning, it has the contribution of the H machine, and H machine has some kind, has information of this machine loves and Kaushik as well. So some relation is happening when I'm taking doing this kind of learning. And again, I'm telling you, these are not different hidden layers. This is the same hidden layer, but at different time stamp. So this is t equals to 0, this is t equals to 1, t equals to 2, t equals to 3, like that way. Now you see, whatever the sentence you just create, so I'm just keeping over here 4 words, you can create 8 words as well, but the network is not going to change. So every time the more number of words it will create, so it will try to keep that sequence, it will try to make that sequence. Okay, because every word has some relations with its previous words as well. So this is how a general RNN works. Now there are some kind of attributes you have to see. So the same thing that you I just repeated that architecture. So every time some predicted values will be created, and as there is prediction, so definitely there will be some loss, and the total loss will be counted as the sum of all these 4 loss. Now, definitely the target would be what? To minimize the loss. Again, gradient descent algorithm we can utilize, as it is very much simple. Any other algorithm also we can utilize for the minimization purpose. No issue. Now, when the loss for this particular sentence is minimized, then we have to train with some different sentence and goes on. That way, we will be training with different types of sentence so that network can learn different types of analogies or different types of relations between the words. Okay, let's say we have 100 words in our training set. Now when these 100 training samples we have fed through this network, then we will say that is in one epoch. Okay, so epoch versus by epoch, the loss will be reduced and your model will be trained so much properly. And you see why we say it this hidden layer as the memory cell, because it is memorizing some information of the previous words as well. So this is the basic knowledge about how RNN actually works. Now, definitely there are some kind of drawback of this RNN, because that is the first recurrent neural network is the category of algorithm, and this one algorithm that was been first developed. But you see, there is one problem with that. What is the problem? Okay, before going to that problem, I just want to say that how this representation can be done. So I am just keeping this module over here. So often we represent this way. So this is the hidden state coming as the input to this hidden layer. This is the input and this is the predicted output. and it will generate also the next hidden state. And what are these circles? As I told you, these are nothing but neurons. So each and every neurons will perform the linear sum followed by activation. Linear sum followed by activation. And in general, like for activation function, we utilize tan hyperbolic function for RNN. I told you sigmoid was utilized mostly for the feed forward neural network or multi-layer perceptron models, and tan hyperbolic function are mostly utilized for the this kind of RNN based architecture. Now coming to the problem. What is the problem? You see these two sentences. So today, due to my job situation and family conditions, I need to take a loan. The same sentence I am just modifying a little bit. Last year, due to my job situation and family condition, I had to take a loan. Now you see the changes between these two sentences. Here it is today. For that I have the word is need. Here it is last year. That's why the word has to be had. So there is a dependency in the verbs that may happen in the past, like long past in the sentence. Sometimes in the sentence you see like when, so that's what I just try to say, like I gave you the example of with 4 words. So the practical limitation is what I told you, that these kind of RNN, recurrent neural network, try to keep or memorize what are its previous words are, and based on that it will try to predict. Okay. Now if the word length are increasing, say 10 words, 15 words, so that becomes the problem with RNN, because RNN can tackle practically 8 to 10 words. It can memorize or remember. It's a fact. As much the longer the sentence will be, the past words, like the most past words can be forgotten. Over here you see this sentence, this is fine, lot of words are present, but this particular word has a direct relation with the very first word that we said. Now if I am implementing with this kind of RNN, it may not predict what would be this word, or in this case also it cannot predict, it has to be had. So that's the problem. It can tackle with shorter number of words, practically say 8 to 10 words, it can memorize very properly. But if you go beyond that sentence, then it becomes problematic for the RNN. It can lost the memory. So that's why we say it as the short-term memory work. Like Gajni, Amir Khan in Gajni. So if he can remember some short phrases, long-term memories can be forgotten. So how to overcome this particular thing? So what I told you, we have a short-term memory. So this is a hidden state that I am showing. So in this flow path, I can maintain the short-term memory part. And what I need is the long-term memory. So that's why I am jumping from RNN to LSTM. The full form of it is long short-term memory. So from the name, you can get an idea that it is dealing with both short-term memory and long-term memory. And this is particularly a LSTM cell. So it is not a neuron anymore. It is a neuron, but much more complexity, because it has to deal with short-term memory and long-term memory. Like, for example, if I'm just telling you one sentence that don't go outside, it is raining. Now, if you see that if I am obsoleting the first word, don't, then the entire sentence meaning will get changed. Go outside, it is raining. So it is like the entire opposite meaning. So that's why sometimes we have to keep the long past words and we have to memorize them so that the next predictions can be well done. So that's why we have to deal both short-term memory and long-term memory. And LSTM is an improvement on that RNN part. So LSTM is also an RNN, category of RNN. There is another RNN like glue. So I'm not going into that. because we are going to utilize LSTM in our model. So that's why I am telling you what is LSTM. So LSTM is a variant of RNN, much more with much more improvement. Okay, but how long? That is another question. But means when we have to maintain this long memory, what other things we have to consider? Now let us take a long sentence. I don't know whether anyone named Shondeep and Pooja is here or not, but I'm just taking the example of it. See, Shondeep eats samosa almost every day. It should not be hard to guess that his favorite cuisine is Indian. His sister Pooja, however, is a lover of pastas and cheese. That means Pooja's favorite cuisine is Italian. Now you see this Indian, how it is predicting. Try to think. Means if I am asking you, just forget about this particular part, this Indian part. So if I am asking you what is his favorite cuisine, so by looking at the samosa word, you can say that it is Indian. That means this is a key word. We are not memorizing all these words. We are just memorizing these keyword samosa. And that will be a part of this long-term memory. But at the same time, you see when I'm building the next sentence, so this is becoming a paragraph, two sentences are there. So when I'm bringing to another sentence, his sister Pooja, however, is a lover of pastas and cheese. That means Pooja's favorite cuisine is Italian. So we can say based on these pasta and cheese that this cuisine is Italian. It is not Indian. But how the machine will understand? Because machine is storing samosa in the long-term memory. So how it can predict Italian? So that means that algorithm has to forget this word and take new inputs, pastas and cheese. So long-term memory with forgetting factor. So that is the another important aspect of the LSTM cells. So four important things over here present: short-term memory, which we say it as the hidden state; long-term memory, which we name as the cell state, like it's a kind of abbreviation that we utilized, or some kind of say technical jargon, you can say. Forgetting factor, we say it as the forgetting gate, and new input, that is the input gate. So what we understand, that definitely we need some kind of long-term memory, and long-term memory means we do not need to remember all the words. We need to identify some keyword, and that has to be stored on the long-term memory. But how is it only good enough? No, because at the same time, when we are dealing with really long sentences, then we may have to alter this long-term memory as well based on the newer keywords. So this old keyword has to forget and new keyword has to include or input. So this makes the entire part of this LSTM cell. And if you just technically draw the diagram, the operation, this is a LSTM cell. It's a little bit complex, but yeah. So this is the input, hidden state, some sigmoid operation. It will help us to forget the previous memory. Then some new memory will be added. How it will be added? Based on the input and the hidden, again tan hyperbolic and sigmoid function, and it will help as the to add into the cell state. And how the newer hidden state will be given? So again input and the previous hidden state, it will be sigmoid and tan hyperbolic, it will gives us the current state. So I'm not going exactly how this operation. If you want to really, if you're really interested, you can go to this link. This is a very well like literature you can follow, like it describe a lot of different equations very well. So I practically myself have followed these things when I started with this LSTM thing. So I it's a very good read. Okay, you can follow this one. Now let us talk about the autoencoder. I already said you that this is a kind of representation layer it will create. Let us come back. Let us, with this knowledge of neural network, let us come back to what we have left. So what we started with, let us memorize again. We tried to develop one machine learning model which can identify whether a particular sequence is resistant to which group of antibiotic. Okay, so, and this was the network architecture. So now you see in this autoencoder, instead of providing simple neuron performs only summation and activation function. We put LSTM cells at the different neurons. Not only that, we make it deep encoder and deep decoder. Deep in the sense, if there are more than one number of hidden layers present, we generally refer to as the deep layer. So this is two hidden layers are present, and each hidden layers are multiple number of LSTM cells inside it. The decoder part is just opposite to this encoder, because the idea of this decoder is how well from the representation layer it is creating the original data. So when the reconstruction loss will be very much small or close to zero, then we can say that the representation layer is very exact or good enough. Now that representation layer will be utilized for this feed forward network, where these are the simple neurons. Sorry, this is not neuron, this is the input layer where this matrix will be fed as an input. Now these are the hidden layers where sigmoid, summation, linear sum and activation functions will happen. And finally, we'll get the class output. So these are the network operations that has been happened. And these are some kind of model parameters that we need to tune to get the optimized result and very good accuracy like that thing. Okay. So now with this thing, let us go to the result section. You see, so we named our model as the Stalinate. Okay, I forgot to tell you. So Stalinate stand for Stacked LSTM Nested Deep Autoencoder Network. LSTMs are stacked, it is deep in nature, then ultimately it is doing some kind of classification. So this autoencoder is actually for feature extraction. This representation layer is extracting the features, important features from this input data. Based on that feature, then there will be a feed forward neural network which will do the ultimate classification. Okay. So this is the performance score on the cross validation data. You remember why I told you the data split? First holdout, 80% was kept for the training and 20% was kept for the testing. Then for the 80% we utilize the cross validation. So this is the cross validation output. So these blue, these are for the five bacterias. The sixth one we could not implement it because RGI did not able to give us any kind of class information. So as there is no class information present, so we cannot develop any kind of supervise. So we just keep it off. We have worked with 5 different bacteria over here. Okay. So this is the this is the accurate results with the 4-month data. This is the accuracy with the different metrics: accuracy, specificity, precision, recall, F1 score with the 6-month data. And these are the results with the 8-month data. You see, for all the results, they are nearly 90% accuracy and specificity we are getting. So this is some kind of summarization of the thing. I will share my slides, and because I think I'm just running below behind the time, so I'm just skipping this part. You can go through. This is just summarization of the performance scores. Well, this is the ablation study. Ablation study is generally what we do when we develop any kind of neural network architecture. Here in this neural network architecture, you see LSTMs are there, autoencoder is there, then there is a feed forward network. Now the question is, what happened when individually we utilize them? Like you over here see vanilla LSTM. like a simple LSTM, how much accurate result it can give. Autoencoder with simple neuron, like the neuron which can perform linear sum and activation. So this is known as the ablation type study. Means every part of the network, we are taking it as it is own, and we are trying to see how accurate result it is giving. So every time you see how much increment we are getting. So with autoencoder, 79% of accuracy, and vanilla LSTM, we can get about 76% of accuracy. But Stalinet, it is giving us like 89 more 0.6% of accuracy. But definitely you have to remember that the processing, the computational time or the training time is quite huge for this Stalinate compared to this like ablation models, because these are very like easy models, so they can easily learn on the data. There are a lot of computations are present in the Stalinate architecture, so that's why it is taking a lot of computational time to train. But definitely, if this is the increment in the accuracy, we can like expense that much of time in the training purpose. Okay, so this is the comparison with the SOTA, like state of the art models. So like there are some kind of existing models present which can perform similar kind of task, but yes, they have some kind of drawbacks which we try to overcome over here. So like Fargene, RaceFinder, XGBoost, CART. So these are all machine learning based models. And what we have developed is the Stalinate. So for 5 different bacterias, we have implemented these different algorithms and we have made some comparison, and we see like how good enough our algorithm with existing models. And the last one is the validation, because I told you we kept the 20% test data for the validation part. So here, this one is the validation scores. Okay, with these data, they are not even taken given as the input to the model for the training. The purpose of validation is we directly do the testing. No training is done, because training will always improve the accuracy. What happens when the model will actually see a new data? Then there is no time of train, only test. During the phase of testing and deployment, we do not do any kind of training. That's why we make separate the data as a whole. We do not alter anything. We do not take any sample of it for the training purpose. Okay. So this is the validation set data, which was not exposed to the training phase. And for them also, it is the model is showing some very good results. So these are some of the summary of these things. And I have I would like to acknowledge like the agencies like ICMR, WBTSTBT, and ANRA for funding our project. And these are my students who are doing PhDs and masters. So these are the master students and these are the PhD students who are working with me. And these are the faculty members, because I told you, like as I said, I'm background is my in electronics, so I have very limited sense of biology. So I need people who have a very specific domain knowledge. So these are Dr. Rachana Banerjee, Dr. Sundip Pal, and Dr. Sujay Chattopadhyay. I'm working with them to collect, because I'm also learning this bioinformatics. You know, after I joined, like since 2022, I started exploring this particular field. Before that, I used to work in the medical image analysis as a whole. So it's quite interesting, and the field is very uh, gives me some kind of enthusiastic feel, because a lot of things can be happened over here. So there is a lot of opportunity in this particular field. So with that thing, I would like to share some kind of this particular site. If you are interested in machine learning or some application related to machine learning, so you can some kind of you can find different challenges or toolbox, or you can socialize in the online forum as well. Particularly some of the things I also follow to get enriched, because in the field of AI, it is evolving per hour or say per second. Every time I'm spending the time with you, a lot of algorithms has been developed. So thank you very much for this particular present for patiently hearing this entire thing. And I would like to quote. I saw this particular another way of this quotation in Professor Kishore's lectures as well. I really I like that thing. So AI will not replace you, but a person using AI will definitely, because today's age is AI. Okay, so now let's quote. I'm going to share with you one tutorial from where you can get the detailed hands-on about the code, the elaborations, detailed elaborations on the code, step by step, what module is working, what I will share everything. I have prepared one thing. So this is the tutorial stuff I'm going to share with you. But for the time being, I just want to show you some code of it. So can you see me? Can you see this particular screen?
Yes, yes.
Okay. So I'm utilizing Jupyter Notebook over here because I think like Orun Abu sir and like Obhijit sir also, they have utilized Jupyter Notebook to teach you the Python things. So in the Python, so first, if you would remember that we need to install some sort of libraries. Okay. So here, this particular instruction will install this TensorFlow, scikit-learn, then imbalanced learn and OpenPyXL. So TensorFlow is basically utilized to build up deep learning models. Scikit-learn is basically utilized for pre-processing and evaluation, because what are the different functions I'm going to call, they are a part of these libraries. And imbalance learned is actually provides additional evaluation metrics like specificity and all. And OpenPyXL is used for the read Excel file read, because okay, I told you that I'm going to show you the KMR matrix. So this is the KMR matrix, not for the whole. I am showing you a part of the data for a specific bacteria only, because if I am going to show take the entire data, it will be like lot of time. So this is the KMR matrix. You see, these are the counts, and this is the feature. So format data is present, and at the end there is class labels. So it is already encoded, level encoded. Okay. So there are different class labels are present as well. So based on that, we can create some kind of thing. So 1 zeros are maintained over there. So now going back to the code part. So if I would run this thing, yeah, so yeah, so all the libraries has been installed. Now the next part is the importing the libraries from these installations. So I hope you know about NumPy, Pandas, all these things, because they have already been discussed in the previous classes. So sklearn also. Okay, for the simplicity sake, like NumPy stands for the numerical operations. Pandas, they are actually helping us to handling the data. Pre-processing, like from the sklearn, we are importing pre-processing because we are going to utilize level encoder and standard scaler. So in the last lecture, you have come across the standard scaler where we normalize the data, input data. So here also we will do the same thing. The input data will be normalized with respect to zero mean and standard deviation value. And then label encoder, we need to convert the input label, the class label into the numerical values. Okay. So now, then k-fold cross validation, because we are going to train the model using k-fold cross validation. So that's why I'm importing this as well. Okay. Then performance evaluation metrics. For the performance evaluation, we need metrics, these libraries. So these are the precision score, recall score, which I am importing from the sklearn. Then IMB learned, from where we am incorporating the specificity score. Then TensorFlow, Keras, This I am importing because we need to develop some kind of deep learning model, and generally TensorFlow, Keras, they are helping us because using them the common syntaxes will be very much less. Without them also I can create, but they have some kind of inbuilt functions which help us to directly give the input to the different layers. Okay, so let us run this particular part. Okay, so now load data. So data I am loading from my computer. I am telling you that I told you I am just utilizing for one bacteria, even some part data, not entire the one, because otherwise it will take a lot of time in the training. So I'm dividing the data into feature and label. So X represents the features, the KMR features. And the last column, which is known as the Y, I am keeping it as the class label, means the antibiotic groups for which the sequence are resistant to. Okay. So let us run that particular thing. Yeah, it ran. Then here I am doing some kind of standard killer operation like normalizing the data and encoding the output. So whatever labels we have some kind of class information, right? So they are kind of text, some antibiotic names, but the model will not understand any kind of names or any English like words. So it can only understand the values. So that's why we need to encode the labels. So here I'm utilizing label encoder because we have fewer classes only. So I'm utilizing label encoder to encode it into the classes, and standard scaler to make it some kind of standard normalization. Okay, so now here is the autoencoder part. So you see 150 dimension to 50 dimension it is converted. So this in this auto encoder part, so input dimension and input layers. So basically this input layer is defined based on the number of features present in the dataset. Like I told you, how many number of features, based on that the input layers will be defined. Now we have to model the encoder part. Encoder part will be dense. Activation function is utilized as ReLU, and we are utilized batch normalization and some dropout factor of 0.2, because what happens, encoder is converting the data from 150 dimension to 50 dimension. Now this is not going to happen in a single stage, because I told you we are utilizing deep autoencoder, means there are double hidden layers present. So that's why I'm putting some kind of dropout factor. So from one hidden layer to another hidden layer, there will be a dropout factor of 0.2. Okay. And there will be, so second dense layer for which will be of size of 50 dimension and activation function. So this is the representation layer that I told you that comes in the between, the latent layer. Then from the latent layer, we need to create the bottleneck. Bottleneck is actually some kind of compressed representation, the representation from which we can find out what are the important or significant features are present. Now then there will be decoder. So decoder will be just opposite, you see. So from 150 to 50, then from 50 to 150. Same function over here we're utilizing. And we are taking the bottleneck data as the input. And all these things are becomes very easy because over here you see I am utilizing Keras, this particular library. Otherwise I have to write a lot of lines of code. And as we are taking these libraries as the input, so its layers I can directly utilize these functions and define it. Then there would be output layer, and output layer will be what? It's a kind of dense model. Okay. Then we need to train the autoencoder by giving the input as X scaled, epochs 30, batch size 64, validation split 0.2. So these are the parameters that I talked to you about during the, and these are said as the hyper parameters. uh, I forgot to tell you that there are two kinds of parameters when we are dealing with this kind of deep neural network. One is the model parameter, like the weights, bias. These are need to be trained during the training process. Apart from that, there are some certain parameters as well, like how many number of hidden layers should be there. In each hidden layer, how many number of neurons should be there, then what should be the learning rate. So these parameters cannot be trained during the normal training process. These are known as the hyper parameters, and these hyper parameters can be trained by using some kind of grid search training. So in Python we have a dedicated function or code present which is grid search cv. If you can call, what you have to do, you have to give some kind of matrix, and if when you call that function, it will gives you the a kind of optimized values of these hyperparameters. Then we need to extract the features, like from the encoder output, whatever the bottleneck it is generated. So from their bottleneck we are creating some kind of features, because we need to give this as the input to the deep classification model, feed forward neural. So that's why we are creating the encoder model over here and x encoded. So let us run this particular part. So over here you see epoch wise it is giving how much time and how much loss. So every epoch wise you see the loss is minimizing. So for 30 epochs we have chosen over here. So the loss becomes last 0.1926. So at the very beginning the loss was 0.7255. It was pretty huge, I told you. But at the end you see the loss becomes very small. Now let me just clear this cell output. Then there will be classification. This is the final part. That means the feed forward network. So the feed forward network, we utilized k-fold cross validation, or like 10-fold cross validation over here we have utilized. We create some open matrices like accuracy, precision, recall, F1 score. Now for each k-fold, because I told you in the k-fold strategy, say you can choose 5-fold. I have chosen over here 10-fold. So generally 5, 10, these are some standard values. Most of the research papers they follow. You can utilize 8-fold as well, but standard 5 or 10-fold. Okay. So we have utilized 10-fold over here. So that means 10 buckets will be created, and in each fold 9 buckets will be utilized for training, and the rest 1 bucket will be utilized for testing. So every time for each fold we will get all these accuracies, precision, recalls and F1 score. So that's why we have created some kind of array matrix over here. Now X-train, X-test we have utilized as the X encoded. That means this encoded result that we got from the autoencoder representation layer, that will be given as the input over here. And corresponding Y encoded also we are giving as the supervised labels. Now then there is some kind of model parameters, like how dense it will be, what will be the activation function, and dropout percentage. Then again for the layer 2, the dense number of neurons, activation function, then its dropout percentage. So that's way we are creating multiple layers over here. And next is the optimization. So a famously utilized optimization process is ADAM. I told you like gradient descent is the very basic one, but apart from that, there are multiple number of optimization techniques is present. Mostly whenever we are dealing with deep neural network based optimization techniques, we follow this ADAM architecture. It has some its own uh, like uh, uh, like pros sense in the sense. So now all the stopping criteria, patience, with pipe and restore base true as true, and these are the evaluation platforms. So evaluation, we are measuring this accuracy, precision, recall, F1 score, and specificity. So from the matrices, the arrays that we have gathered, so from there we are averaging it and we are collecting their average value over there. Here. Okay. So if you just run this, so this will generate, this will take a little bit of time because the classification is happening over here. Yeah. So I think it is done almost. Yeah, it is done. Then the last part is the results. Here we are like printing out the results in both mean and standard deviation format. So this is the accuracy, precision, recall. This is the average value and this is the standard deviation values. So this is all about the code. I cannot, I think I'm out of time and I need to stop it over here. And if you have any questions, then I'll be really happy to answer.
What a
Thank you.
fantastic lecture by Dr. Kausik Basak. I really appreciate this. So let's ask some questions. Audience, please ask some questions.
Thank you, Kishore sir.
Yes, if you allow, can I please ask some questions?
Yes, yes.
Sure.
First of all, this is
Can you be a bit more louder?
yes, sure. Can you hear me now?
Yes, yes, yes.
Okay, first of all, this is a fantastic lecture, as Kishore sir said. I really enjoyed it, and it was, I mean, fantastic. Thank you so much for such a lovely session. Uh,
Thank you, King Kong.
Thank you so much.
Any
Yes,
questions particularly you have?
yes. I do have two questions. First of all, as you were saying about LSTM, uh, to forget about some steps, that is after the previous declaration. My question is, why can't it memorize the previous sentence? I mean, suppose you were given a
The
particular.
entirely the memorizing the previous sentence entirely, are you saying?
Yes, I mean, if what if there is some more one more layer to memorize, particularly for memorizing the previous inputs,
See,
so that.
memorizing mean you need to store all those vectors. You see, the word it is memorizing that I am just
Mhm.
simply representing, but actually it is the vector it is storing its memory. So now, when lot of words are happening, so some contribution of it will reduce because that's what I just told you. If you
Mhm.
just go through that particular link, you will understand that then there is a sigmoid activation function and then there is a tan hyperbola activation function. Okay. Now, the sigmoid activation function provides output between 0 to 1. So
Mhm.
if it becomes negligible, then when the time needs to forget, then definitely the output will be close to 0. And when the time to add, then tan hyperbola functions will be highly fired. So now if you want to memorize each and every word, then definitely the contribution of these two will be very much high. So that way you cannot identify that which is keyword and which is not.
Okay,
Okay.
I got it. So
So
that.
that is the main fundamental thing, that identifying the key terms. Because uh, I just want to say this thing. I don't know whether you have heard a bit about or not. From here only, the next modification, the next improvement on the LSTM comes, which is known as the attention. And the future version of the attention with autoencoder is the transformer, and future version of the transformer is the GPT.
Okay.
Okay, so that's how the total evolution of the machine learning model goes. Like the entire thing is, we need to find out some keywords, because if you want to store, so you see right now you can provide say 100 words of paragraphs in the chat GPT, and it will gives you some output. Now, will it happen like you are giving the entire book as an input and it will gives you output? For that, it will require lot of nodes, lot of computation powers, like huge capacity. It may happen in future, but right now not. It can generate some good amount of data, and it can tackle a good amount of data as its input as well. So every time, so that's why it is not it is just the important fundamental thing is we need to identify the keywords and we need to focus on them, not entirely on the entire sentences, because that way like computations will become so much high,
Yes,
and
I
we
totally
cannot
agree.
restrict ourselves only to one or two sentences.
Hmm.
Right now we are dealing with say 100 sentences.
Hmm.
Okay, so now storing all the things will require a lot of time or a lot
I
of
understand. Yes, yes, I
computation.
got it. So, storing the keywords only will be computationally efficient and less time consuming as
I don't know, means your voice is becoming very feeble actually.
well. Okay, okay. Actually, I am having a lot of network issues. Am I visible? Am I audible right now?
Yes, I can hear you. Yes.
Okay, okay. And one more thing is that you are talking about that I mean sequence of bacteria that is appearing that is affecting the human bodies and
What
analyzing those
sequence of?
sequences. So the bacteria you are talking about escape
Yes,
particularly.
yes.
So I am wondering how the I mean how are you incorporating the initial condition or the outside constraints, like for example the weather condition, the way the escape will affect human body in the hill areas, like in, for example in Kashmir, it will not the way will not be same in Rajasthan. So how will you incorporate the initial condition or the outside constraints, for example, in this case, the weather condition?
Okay, okay. So here we are not incorporating that particular knowledge. That's a very good question actually. So based on the demography, I think you are saying the repercussion will change, right?
Yes, demography wise, or in other systems, some other outside constraints can happen, can occur.
Yeah, definitely. You see, the entire thing is even for human to human, the effect of escape group is also different. I
Yes,
cannot say a
yes,
particular bacteria which is causing some kind of illness in my body will definitely cause illness to you, because that we have seen also in case of COVID. Although it's a virus, but we have seen it. It is not the representation. The biological representation will be different from one human being to another. What we are targeting over here for the patients which are suffering already have known suffered identity for different kinds of things. So here definitely we are not incorporating the people who see bacterias will be there. I'm not talking about that thing. When it is causing some harm, that is the point that we need to keep a step out with some kind of mechanisms, right?
okay. Okay, I got your point. So you were saying that after the
Uh,
system that
Kinkar, are you okay? Okay. So, being the commoner and being the novice person, I want to ask you some trivial questions regarding the data acquisition part.
yeah.
You have downloaded the data from NCBI Genome database, right?
Yes, yes.
Have you paid for this or it is free?
No, it's free. It's absolutely free. It's free for
Okay.
everyone
Okay.
who have the money, sir.
Okay. Now, the next question, next trivial question is regarding the bias and linear sum part. So,
Hmm.
why didn't you take some polynomial which is non-linear? Then you couldn't use the bias term.
No, 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 no. Bias term is present in the linear sum. It is not present in the that activation function. The linear sum is the linear operation. The linear and nonlinear operation are done separately.
No, okay, but why do you need the nonlinear term? Because
Nonlinear, like,
if
see,
you use if you use a polynomial, there is nonlinear term. So why do you need ReLU function? Why do you need sigmoid function and so other activation functions? Because this polynomial will give you the nonlinearity, right?
definitely. But the thing is, like, this is the better way, I think, that how to choose which polynomial will gives us the good answer. So that's why this particular, some few sets of activation functions, I believe it was developed, like sigmoid. It is mostly used for this kind of deep classification purpose, feed forward layer. So it can gives us values between. So if you just look for each and every neurons, the ultimate goal is what will be its contribution to the next layer, whether it will contribute in a more positive sense or in a more negative sense. So sorry, in the there will be null contribution, because for sigmoid the output varies from 0 to 1. So that's why it's a kind of nonlinear value. But if you talk about polynomial, then which particular order of polynomial I should utilize, that will be a question, because from problem to problem the polynomial order can be different. And now to find out which, what will be the polynomial order, that will be again another hyperparameter I'm adding to my like network. It can be used, but I think that adding another hyperparameter into my design, it will be more challenging.
Yeah, number of parameters will increase actually.
Yes, yes.
And the third part is what kind of encoding did you use? It is one hot encoding or something else?
For which one?
For your identification of antibiotic part. I mean,
So for classes we have utilized the label encoding,
okay,
and for sequence data we utilize the KMR encoding. That
okay,
4 bar I told you. So,
okay. I think Dr. Amit Chatterjee has a question. Amit, please.
Thank you, Kishore. It's not exactly a question. I think there's just a little bit of clarification.
yeah, surely, sir. Hello.
Sorry, I think I deactivated myself.
Okay.
The clarification relates to the fact I think there was a little bit of a mismatch between what Kishore asked and what you answered. I think Kishore was asking, just for a second, Kishore, correct me if I'm wrong, just for a second. So let's say we are given a lot of data and we are allowed to make any sort of an approximation, completely forget machine learning or any learning. And if we are just allowed to go up in the polynomial ladder, basically going up to any high order of polynomial, we can fit any data with that. And it's pretty much good old extrapolation. And then why exactly do I need to paraphrase an activation function and the mathematics of that? Kishore, is this what you asked?
Yes, exactly.
Right. The answer to that is, I think partially the answer was given to you, which is just imagine how many such parametric, how many such parameters you would need to add in the process. But there's a more important and very fundamental issue here. Extrapolation is not a probabilistic mathematical fit. So what that means is, so imagine that you have got a perfect fit of the profile of the features of anything that you wanted to from the entire set of data, but that not being probabilistic, that will not allow you any sort of a prediction on the same manifold if you have a new set of data. So that's the main problem. And the way people can handle that is basically going into the realm of Bayesian inferencing. So something like a Markov chain Monte Carlo,
Yes,
where you
yes.
can make, well, polynomial or otherwise, you can parameterize each parameter in a probabilistic forward and backward mapping structure. And that will allow, using Bayesian inferencing, and that is exactly what will allow you to make it, well, give it a probabilistic fit. The way the structure here works, the activation function structure works, I think a very good example of that is the support vector machine, where you have a high dimensional space and you want to pipe the information from the high dimensional space with minimum data loss into a low dimensional space. Low dimensional meaning lower number of parameters. So if you look at the way the thing is structured, W transpose W, that's basically a vector multiplied with a vector. And essentially in the vectorial level, you have a quadratic order. So basically, no matter what sort of high order nonlinearity you may be having, you are approximating the high order nonlinearity using a quadratic vectorial map. That's pretty much what the role of the activation function is. If I am wrong, please correct me, Kaushik.
No, sir, absolutely right. So in SVM that we have seen, yeah, the quadratic equation formulation itself, it's very much challenging.
Yes, because I mean, it depends on which side of the bargain you are in. So you have the, you have the design, you have the boundary, and depending on how close to the boundary your parameter space allows you to go on to, your approximation or prediction will be that much accurate. And there's very little control if you have quite a few different parameters. Anything more than 3, to my understanding, is very, very difficult to coordinate and manage.
Absolutely, absolutely, sir. Thank you,
Sorry, I
thank you.
just thought about adding this little bit.
No, sir, thank you very much. It's a very
Welcome.
enlightened answer.
Thank you, Amit. So, any other questions, please? Time is very short. So, I think there is no other questions. So, respected audience, it is my privilege to propose a vote of thanks for this session today. On behalf of Department of Physics, Prabhu Jagat Bandhu College, I extend our heartiest gratitude to our speaker, Dr. Kausik Basak, for gracing us with his presence. Your insightful talk were truly captivating and have left a lasting impression on all of us. We particularly valued your perspective, which provided a completely new outlook. Thank you for taking time from your busy schedule to share your expertise. Thank you very much. So,
Thank
good
you,
night.
sir, for providing me the opportunity to present this. And definitely, I'd like to be a part of more future workshops if you are organizing, and
Sure.
give you some more novel kind of novel, or say interesting some solutions in this
Sure,
aspect as well.
sure. So,
Thank you everyone for patiently listening. I know this is the time has been taken too
no,
long, but
it's okay. It's okay. So, we will meet tomorrow again. So, for this, good night for all. Okay.
good
Thanks.
night, everyone.
Good night,
Good night.
everyone.